Starting from today, we'll spend a few classes discussing about the subject of solid modeling. So far, we have been discussing about parametric curves and surfaces. So, now we'll take up the solid modeling as a subject. Okay. There are many ways of modeling solids, and many of these methods are very different from what we studied in curves and surfaces. So, let us look at them briefly in today's class, then we will take up more details about these models and methods in our subsequent classes. Okay. Now, one of the logical extension of modeling solids is basically extension of parametric curves and surfaces, which we discussed, to solids also. Just like we had a Hermite curve and Hermite patch, I may have a Hermite hyperpatch, which is nothing but a piece of solid which is bounded by 6 surfaces, and you can have 3 different forms, just like we had for curves and surfaces. I can have algebraic form, in which if any coordinate, let us say x, y or z, is a function of u, v, w, and you will have all the terms like up to u cube, v cube and w cube as a part of this. So, I can write down the algebraic equation, and that may be one of the ways to do that, or I can have geometric form, where I can define, let us say the input will be in the form of 8 corner points of a hyperpatch, then first, second and other derivatives at those 8 corner points. If I provide this as an input, I can also construct a geometric form of a hyperpatch. Then one can also define an endpoint form, just like we have a parametric cubic curve, which is defined by 4 points, interpolating 4 points, or I have a bicubic patch, bicubic Hermite patch, which is defined by interpolating 16 points in a space. So, I can have tricubic Hermite hyperpatch, which is defined by 64 points, that is 4 into 4 into 4, a matrix of points. So, these are like one way of looking at solids. Then the definitions can be extended to Bezier hyperpatch or B-spline hyperpatch, and also NURBS hyperpatch is this thing. This is not a very convenient way to model solids, okay, because most of the solids which we come across, particularly in engineering applications, are not free-form solids, okay, and so it is not a very convenient way to model the solids. Suppose if I want to model a simple cube, this thing, a NURBS hyperpatch representation would be a very difficult way of looking at a very simple solid, okay. But it has its own applications, particularly in computer graphics and others. Hyperpatch representations are used, like one of the applications is in computer animation. Suppose I have a solid, and this solid undergoes deformation because of application of, let us say, forces or collisions. So, the deformations can be which basically have a complex shapes, can be represented using hyperpatch kind of representation. So, it has applications, but not widely used method of modeling solids. When it comes to solids, particularly for example, most of the solids which we come across, particularly in engineering applications, are relatively simple, okay. They are like either extruded shapes or shapes which can be very easily generated by parametric directions, which are like line and circle. So, which we usually call as a prismatic shapes. Those are the more common forms. So, we look at other ways of representing solids, moving from hyperpatch representation. One of the first methods of modeling solids which was introduced, is called as a primitive instancing. In fact, when solid modeling was in the beginning, particularly in 60s and 70s, when this subject came up, primitive instancing was one of the first proposed models to basically construct a solid. So in primitive instancing, what is done is a part is modeled as a combination of primitives. Like if I want to construct an object, it should be treated as a combination. That means many primitives put together side by side are connected, kind of a thing. And the kind of objects which can be modeled will be defined by how many primitives you have. Okay. It's like I can have a gear as a primitive, or I can have a spring as a primitive, or suppose if I am constructing a mechanical object, I will directly take these primitives and define the parameters to specify primitive uniquely and place them in a space and build more complex objects. So one has to make basically a mental picture of, given a particular object, what primitives are needed and how to put them together in order to get more complex objects. And whenever like there is an object, one has to model an object where the given primitives are not sufficient. So one has to introduce new primitives also as a part of a library for modeling the object or for future applications. And in order to define a primitive also, like one has to give a certain minimum number of parameters by which a given primitive can be uniquely defined. That was another thing. So I will explain this using, let us say, an example a little later. If I take an example, like I may have in my library a primitive which looks more like a cuboid. Now this is a primitive. As far as size is concerned, you have a variations are allowed. As far as shape is concerned, it has a fixed shape. So this is primitive which is stored in library. Using this as a primitive, I can construct any of these things. They are all instances of the same primitive. Okay. Once I have a primitive like this, I need not have other primitives which are just variation in terms of sizes. Like take an example of primitive like this, which is a rectangular parallelepiped or cuboid. One can very easily define this primitive using 3 parameters. Okay. Somebody can call it as length, breadth and depth, or length, breadth and height, or whatever it may be. So 3 variables are enough. By varying these 3 variables, okay, I get very many instances of this particular primitive. So if any object which has this kind of primitive which is needed, so I will just vary these values and get any of the size variations as far as primitive is concerned. But suppose if I want to construct, let us say, another object which instead of having a, let us say, a rectangular cross section, let us say I have a hexagonal cross section, then that becomes a different primitive. I cannot model. So you need to have another primitive in your library in order to do so. So that is like a very, you can say, non-trivial or you can say, or rather trivial way of modeling the object. Like here is just an example. I may also have a primitive like this. Okay, this is again sort of rectangular parallelepiped, but you have a cylindrical through hole in it, which is like one type of primitive. Now in order to define an object like this, I choose certain minimum number of parameters, so that I should be able to get the instances of this primitive. So how many values are needed in order to basically store this kind of primitive uniquely? Like for a parallelepiped we had 3, here those 3 values are anyhow they are needed. Apart from this, you also have a cylindrical through hole, so you need at least 3 more values. Okay, that is in order to define, let us say, center of this particular hole, which may be in the center, it may be anywhere on the solid, and also what is the diameter of this particular hole. So a 6 values, 6 parameters will completely define this particular object, and by giving different values of for these 6 parameters, I get many instances of this kind of primitive. So this is shown here, like this is an example primitive which we are looking at. So I have one of the dimension let me call it as d1. Then d2 is a dimension where center is measured with reference to one of the surfaces. Then d3 is the other dimension, d4 is the center distance from another surface. Then d5 is the diameter of this particular hole, and d6 is the depth of this particular thing, depth of hole as well as the object, because it is a through hole. Suppose if I want to represent, let us say, a blind hole, I may need another parameter which becomes like what is the depth of the cylindrical hole which I have. So, since I am calling an object with a through hole as a primitive, okay, this cannot be used to represent a blind hole. So, you need another primitive to do that. Okay, that may be that you call as another primitive which is stored in library. If I want an object like this through hole, I will pick this as a instance, that is primitive, otherwise I will choose the other one. And by giving these values, I can this thing. One can also impose certain constraints in terms of parameters. Okay, like you say that okay, there are d1 to d6 are the values which one has to supply in order to build an object, but in order to supply input, you also have certain constraints. Is that either I can have mathematical constraints, like you can say that d2 should be less than d1, or d2 should be less than d1 and related to d5. So, I can have a mathematical equations, or what you call as the relations, which will define a relation among these parameters. So, whenever you are giving an input, you can give the 6 inputs, but the input should also satisfy those constraints which are imposed. If it does not satisfy the constraints, then instance or a primitive cannot be successfully modeled, or it cannot be used or displayed as a part of this. So, when you have a case like this, it is also called as a constraint based modeling. Okay. So, it is a primitive instancing, but you are apart from the variables which uniquely define, you are also imposing a constraints in order to do this kind of a thing. So, this is like you can say one of the simplest way to model a given solid is that have library of all possible geometries which you are likely to encounter in future, and build more complex object as a combination of these things. We discussed about sweep when we were discussing about parametric surfaces. Sweeping is a concept which can be applied to curves, surfaces and solids. A point which is swept along a curve is, let us say, along a path, gives me a curve. If I take a curve or let us say a straight line and sweep it along a certain curved path or straight path, then I get a surface. So, the same thing can be extended to solids too. Let us say if I take a plane or let us say a surface patch and sweep it along certain trajectory, then the volume which is swept by the surface is a solid. Okay. So, that is one of the ways to represent a solid. And an interesting thing is like you can say the object which you are sweeping need not be a surface, it can be another solid too. Okay. I can take one solid and this solid is swept along certain path. So, volume swept by the solid which you are sweeping is also another solid. Now, this is this kind of concept is used extensively in many engineering applications, particularly in virtual simulations, etc. For example, let us say I want to depict motion of a tool or the volume swept by a tool. Tool itself is a solid. So, tool is moving along certain path, straight line, circle, circular arc or some other trajectory. So, the volume swept by the tool is also a solid. Okay. Or there are two objects which are moving in space and I would like to find out whether they collide or not. Okay. So, what you do is you model the objects which are moving, you also model the path along which they are moving. So, since a solid which is moving along a certain path gives me another solid, I can construct the volume swept by the two solids and see whether the volume swept by the two solids intersect or not. So, that can be used to check whether in a situation like a motion modeling, whether there are any collisions which are happening or not. Of course, among the sweep representation of solids, just like curves and surfaces, there are two of special interest. One which we call as a linear sweep. If I take, let us say, a polygon or a surface and sweep it along a straight line, the object which I get is an extruded object, and or I can have a circular sweep, and where the object is swept along a path of a circle or a circular arc. So, I can have a solid of revolution, which may be a complete 360 degrees of revolution, or it can be a partial too, are special cases of a generic sweep. And there is also a convenient method for construction and storage of solids. Like when it comes to solid modeling, we will see that there are different types of representation. Some representations are very convenient as far as constructing the object is concerned. Some may be convenient as far as storage of the object inside a computer is concerned. Third may be you are also looking at how easy to calculate certain volumetric properties from this particular object. That means, if I am doing some computational geometry related calculations, so there may be other methods which may be convenient. So, it is also one can say, we will conclude later, that there is no a universal or a single representation which will give all conveniences. Okay. So, there are multiple ways of modeling solids, and one may choose to use more than one representation for a given application, depending on what you are trying to do with this solid model. So, as far as sweeping is concerned, it is a convenient method. I think you may have used packages like CAD/CAM packages, where you use extrusion and revolve kind of terms, which is nothing but you are representing an object as a using a construction method as a sweeping in order to build more complex objects from simple geometries. So, and it is also easier to store. That is because I have to store basically what I am trying to sweep, a polygon or a surface or a solid, and also the path along which it is swept. If I am able to store these two, I have stored the entire solid representation. Okay. From these two inputs, I can generate other representations, or I can display the object. So, I can do many things as far as sweeping is concerned. So, sweeping is a logical extension what we discussed in for curves and surfaces. One of the methods which was introduced particularly in 60s and 70s is called as constructive solid geometry. Okay. Now, in constructive solid geometry, what is done is one uses certain known simple solids which are called as primitives. Okay. Like there are certain solid forms which we can say that known form of solids with which we are familiar, like cylinder is a solid, or a cone is a solid, or cuboid is a solid, torus is a solid, or a sphere is a solid. So, I can use a combination of these and combine them in terms of Boolean operations. Okay. The three Boolean operations which are used are union, difference, and intersection. These Boolean operations are actually mathematical operations, or you can say geometric operations, which are performed in order to build more complex objects. I will come to that using an example, this thing. And the object which is let me first take the example, then I will come back to this. Like here is an example of building a solid object using constructive solid geometry. If I look at this object, okay, this is an object and it has a cylindrical protrusion, and within this cylindrical protrusion you also have a certain amount of material which is removed. It is to a certain depth, which is also it is like a blind hole, but a very shallow blind hole kind of a thing. Now, in order to, this object may look little complex, okay, in order to build, but this can be easily visualized as combination of many known primitives which are put together by Boolean operations. So, like if I take these two, in fact the entire object can be modeled using just two primitives, a cylinder and a cuboid, or what you call as a rectangular parallelepiped. Sometimes this primitive is also called as a box. There are different names which are used. So I can use box and a cylinder to build more complex object. So first thing is here is basically a object where you have some kind of wedge shaped this thing which has been provided. So I can take two primitives, take a primitive which corresponds to a dimension of this, then another primitive, and place the second primitive with reference to first. That is important. Okay, these are when you say a difference operation or a union operation, these are not scalar operations. So this is basically an operation which you are doing on a set. Set consists of the points which are which a particular object occupies in a space. Okay, so I will take a primitive, I will take another primitive, construct these two primitives, and then place this primitive with reference to this and do a difference operation. When I carry out a difference operation, you are trying to look at material which is there in this but not in this, okay, which gives me a shape like this. Once I have an object, I can model this separately, the cylindrical. So I have two cylinders. Again I have a difference operation. This is a larger cylinder, this is a smaller cylinder which is in the form of a cutout or a material which has been cut. So I will carry out these two difference operations. I have intermediate objects. Now these are combined by a union operation. Union is nothing but basically you are looking at the material which is there in both the primitives, this and this, excluding the including the common volume which is there in both. So I can carry out build an object like this starting from a simple primitives. So if I look back, the resulting model in a CSG is a procedural model, okay, where the representation is in the form of a tree, okay, because if you look at, this is a tree like structure where when it comes to all the branch nodes which are Boolean operators, whereas primitives are basically the leaf nodes. Like all the leaf nodes which you see are the primitives, whereas the branch nodes are all the Boolean operations which are happening. So using these two combination, I can build more complex object. So in a method like constructive solid geometry, again user has to make a mental picture of given an object what kind of primitives and Boolean operations and transformations can give me the desired object, and one has to put together and keep building more complex object starting from simple objects. Now when it comes to a representation like this, in fact one of the surveys which was conducted many years back says that many of the objects, particularly which are used in mechanical engineering, can be very easily built by just 5 primitives. Okay, what are those? A cuboid or a box shaped primitive, cylinder, cone, sphere and torus. A combination of these 5 can give variety of objects. That is also has a close relation with, in fact, manufacturing processes. If one tries to analyze, let us say, many of the manufacturing machines which are used, you have a combination of motions which are linear and circular motions, okay, and these combination of motions usually yield the objects which are also can be very easily built using these primitives. In all these primitives also you have the parametric directions which are either line or a circle or a combination of these in building these objects. And one can also combine Boolean operations can be need not be for only these primitives. I can also combine with the objects which are produced by sweeping. If I take this thing, instead of having one of the known primitives, like one of those standard 5 or 6 primitives, I can take an object which is obtained by another method of solid construction like a sweeping, bring that and carry out the Boolean operation. So this is also then you are actually enhancing the capabilities of the solid modeling. That is true like when you take care of, for example, a package like CAD/CAM package. So it's a lot of sweeping operations together with Boolean operations. One tries to build more complex objects. Then constructive solid geometry is also a convenient method for construction purpose. Okay, like I can very easily build an object, and so what is stored in a CSG is that in order to represent an object, you are actually storing this tree. Okay. All the leaf nodes and all the branch nodes and the operations. So I will be storing a primitive, the parameters of this primitive, and all the operations which are done on this. So this entire tree structure is what is stored. So representation becomes very compact. Even the complex objects can be very easily compactly stored, and it's a very convenient method for constructing an object using a Boolean operation. But it may not be convenient for certain applications. Suppose if I want to know what is the volume of this object, okay, if I want to know that, probably just from this tree like data structure it may be difficult to evaluate. So I have to do certain additional calculations and do that, or I want to know whether this object has any two parallel faces. Okay, this tree may not give me a direct information like this, whether there are two this thing, because ultimately one has to look at the final object and try to let us say evaluate from the final object. We will come back to that. You may have to convert into probably other representations, and then I can know whether information like whether the object has two parallel faces or kind of thing. So there are some conveniences in terms of construction and storage, but there are also inconveniences as far as computational geometry calculations are concerned. Like suppose if I want to display this particular object, I would like to remove the hidden lines. So it's not a very convenient method to do that, because I need to apply special algorithms in order to do that than more simpler algorithms which are available. Now another very popular representation for modeling solids is what you call as a boundary representation. It's more commonly known as BREP. Okay. Now what is done in a representation like BREP is the object is basically represented by the boundaries or the surfaces which are enclosing the boundary of a solid object. So you are not representing the complete interior points explicitly. You say that here are the boundaries. Boundaries has two sides. There is one on the material side and other is a non-material side. So a volume which is enclosed by all the bounding surfaces is nothing but a solid. Okay. So if I do that, that is this type of representation is usually called as a boundary representation. So the enclosing surfaces can be polygons. If there are only polygons, all the surfaces which enclose a solid are planar polygons, then it's called as a polyhedron. Okay. The object can be called as a polyhedron, or it can be curved surfaces, like I can use quadric surfaces, like it can be surface like spherical surface, or it could be cylindrical surface, one of the surfaces, or I can also use freeform surface patches. Like I can say that here is a solid which is enclosed by 6 Hermite patches. Okay. So there are 6 Hermite patches which completely enclose an object, which becomes a boundary of the object. So that's also if I represent a solid using this, this is also one of the ways, and it's called as it becomes a part of a BREP. But basic difference from if you look from other methods which are there, particularly constructive solid geometry, is that every solid information has two things, one which you call as a topology and another is geometry. Here these two are separately defined. These two, what we call as a topology of an object and the geometry of the objects, are defined separately. So what does one mean by this? Probably this requires little more explanation. Like basically the topology of a solid consists of the relationship which are there in terms of vertices, edges, curves, faces and patches. Okay. So how a one particular face or a patch is related with another patch, whether it shares a common edge or common curve is a part of this. And this complete connectivity information is separately stored apart from the geometric information. Suppose I say that there is a curve 1 and curve, let us say I have a surface 1 and surface 2 are having a common curve which is called as a curve 1. So that is my topological information. But what exactly is curve 1? What is its equation, or what are the data which is needed to generate this curve becomes a part of geometry. So these two are separated and stored separately in a boundary representation. Like when you say in a CSG, if I say that I have a primitive has both topology and geometry which are mixed up. Okay, they are not separated. I will give this using let us say an example. Take for example, I have two objects. Okay, here are the two objects, solid objects, and both the objects have 6 faces. Okay, and they have 8 vertices and they have 12 edges. Okay. Now if I number them, let us say number all the 8 vertices, 12 edges and 6 faces, and also try to represent, let us say, how is the connectivity information. Both the objects will have the same topology. Okay. As far as connectivity is concerned, like I can say that this surface, these two faces share a common edge. So same is true with these two faces which share a common edge. So when I store a topology for this, it is same, there is no difference. But what makes these two objects different is geometry. So what is geometry in this case? Are the x, y, z coordinates of the 8 vertices. Okay. Basically the x, y, z coordinates of the 8 vertices which I can solve. So by changing the x, y, z in certain fashion, okay, I get different shape and size objects. Okay, shape also is changing, size is also changing, because earlier it was a cuboid, now it has it may become some other shape. But what is common between the two is the topology, how the vertices etc. is related. Now in order to store an object, what I will do is I will suppose if I want to store this information in a file, I will say that this object has 8 vertices which I call as V1, V2, V3, V4, V8. Then this has 12 edges which I call as E1, E2, E12. Then this has 6 faces, I call it as F1, F2 all the way to F6. Then I take, let us say, face 1. Face 1 is made up of 4 edges, let us say E1, E2, E3, E4. Each edge, one of the edges made up of 2 vertices, let me call as V1 and V2. So I will store this complete information in one place. Somewhere in the end or somewhere at other place, I will store the coordinates of this. Okay, the 8 coordinates of the points which give me an object like this. So this type of representation gives you a separation of topology and geometry, is one of the probably most widely used representation for solids. Okay. If you say what is probably the most can say widely used or most useful representation, okay, every representation is useful at some stage or the other, but when it comes to large number of applications, boundary representation is used. But it is not a convenient method to build an object. Imagine if you have to build a object like a box like object like cuboid. I do not want to give the complete information that it has 8 vertices, it has 12 edges, it has 6 faces, and this is the relation among this thing, and lastly give a coordinate. Okay. So that may be a that kind of input in order to build an object like a cuboid is not a very convenient. but it's a convenient way to store it. Okay, like I may use a primitive called as a cube from a library, but I may convert into a boundary representation and store it as a part of this for certain applications. Like we were looking at some examples. Suppose I want to check whether given object, a complex object has two parallel faces or not. I can easily find out this. So it basically requires looking at the topology and geometric information. Since you have all the faces which are explicitly stored, I can compare the faces and I can say here is an object like let us say if I take an object like this, yeah, there are 3 cases of parallel faces. Here is an object where there are one case of 2 parallel faces. So one can easily evaluate from the geometry and topology information. Same thing from other representations may be more difficult to do. And as I said, suppose if I want to build an object, constructive solid geometry may be a convenient method, but for certain applications boundary representation may be better. So I should also have a method of converting from one to another. So I build using a constructive solid geometry and convert into a boundary representation. So this method is called as a boundary evaluation. So boundary evaluation is a very common feature in most of the CAD/CAM applications. Okay, most of the packages give you an option where I build using simple sweep representations, constructive solid geometry, etc. And then when I want to do certain operations, I also have a boundary representation of that which can be obtained using a boundary evaluation. So this is again a mathematical geometric operation of converting one representation to another, which is called as a boundary evaluation. Usually the most common thing is to convert from, let us say, CSG to a boundary representation. Reverse is not a very common thing. Okay, like given a boundary representation, converting into a constructive solid geometry is not needed in many cases, and neither it is a unique operation. Okay, this cannot be done. Like CSG to boundary representation is a unique, whereas boundary representation to constructive solid geometry is not unique. Okay, if I just take an example, let us say I have an object like this, which is shown on the left. Now what would be a constructive solid geometry representation of this? Somebody may say this is union of 2 cuboids, one which is corresponds to this and another, and I put them together to get an object like this. Okay, somebody may have a different way of looking. They say no, this is a difference operation. I take a larger cuboid and then subtract a material which is corresponding to this and this. So the boundary representation of this object is same. It has the same number of faces, vertices, edges. Geometry is also same. Coordinates are this thing, but I have 2 different CSG representations for this. So since BREP to CSG is neither needed nor it is unique, it is not a usually people do not go from BREP to CSG, whereas CSG to BREP is a very common thing, because that is required in many of the CAD/CAM applications, which is usually done. Then there are methods which are called as decomposition methods. Okay. Like in a typical CSG type of operation, what is done is you combine primitives but using a Boolean operations. Like when I put together 2 primitives for joining or let us say union or difference or intersection, they may be having certain common volume. Okay. So suppose if I am carrying out, let us say, a union operation, this common volume comes only once. Okay, because since the volume is common to both the objects, I do not count it twice. But I can also build an object where I can put together the primitives, okay, where they are non-intersecting. They are not in the form of an intersecting method. Like this kind of methods are usually called as a decomposition methods. So what is done in decomposition method is basically you have a non-intersecting solid primitives are put together in order to do that. There are many variations of decomposition methods, but the two most popular representations or for solids is octree based modeling and voxel based modeling. Okay. Let us look at what are these representations, because there are certain operations for which decomposition methods have an advantage over all the other methods which we have discussed so far. We will look at those also. Like what is done is, here is an object. Okay. Now what you are seeing on the left is basically a boundary representation. Okay. In boundary representation, what you do is that here is an object which is represented by triangles. Okay. Now when an object is represented only using triangles, it is still a B-rep. Okay, only thing is it is a very special case of B-rep. And here is an object which is modeled using what you call as an octree based modeling. We will come back to that, what is an octree based modeling. In an octree based modeling, like what is shown here is basically a two-dimensional version of an octree which is called as quadtree. Okay. In quadtree, what is done is the object which I am trying to represent is enclosed in a square, and the square is divided into 4 other squares, okay, half the size of this. Now if the material lies, then you look for the object which you are trying to represent is a part of any of these squares. Suppose if there is no material in the suppose there is no material in one of the squares, then I do not subdivide this. Like there is no material here, but there is some material here, so I am going to subdivide this portion further, and I subdivide and I see that there is no material here, so I can go back and do this. So this is just a representation, this is not an object which is shown. Okay. If I look let us say an octree representation here, I think this gives somewhat a structure for representing an octree. Like just like quadtree, in which I take a square and divide it into 4 squares, I can take a cube in an octree and divide it into 8 cubes of where the size or the dimension is half that of the original cubes. Now the object which you are trying, suppose if I am trying to model an object, first I enclose it in a cube and divide the cube into 8 cubes and see whether any of these 8 cubes has the material which I am trying to model or not. If it has a material, okay, suppose if there is no material, I am not going to further subdivide, because there is no material. Suppose if it has a material, if it is completely filled with material, the entire cube is completely filled with the object which I am, still I do not subdivide. I will say that there is a cube which is completely filled, but if it is partially filled, I will further subdivide it into smaller cubes. So when do you go for a subdivision of a cube is like, first given a cube I divide into 8, I will check, there are 3 cases. A cube has completely filled with a material, no further subdivision. A cube is completely empty, there is no material, no further subdivision, but it is partially filled. Okay, a part of the cube is filled with the material which I am trying to represent, then I will do, I go for a further subdivision of that. So you keep doing this to a certain depth, which is called as a octree depth. After certain let us say after going to a certain depth levels, you get an approximate representation of the object which you are trying to model. You are not looking at the exact representation. Suppose if I have an object which is free form surfaces, free form curves, it cannot be represented as a combination of planar surfaces. So you are looking for an approximate method of it. So if I look at this, so this is an octree representation of the same object. What you are seeing here are all basically cubes of different size, okay, which are put together in order to model this object. So going from here to here, like modeling an object from, let us say, a boundary representation to converting into an octree model is called as a octree encoding. Okay, this is called as a octree encoding. And as we looked at, there is another version of a decomposition method which is called as a voxel based model. Voxel based modeling has similarities with voxel is nothing but it's basically a three-dimensional you can say element in the form of a cube. For example, you are familiar with a pixel. If I want to represent an image, I can visualize an image as a combination of pixels having different colors and different intensities, which gives me a look of a two-dimensional or three-dimensional object. So, I can also have a volumetric element which is called as a voxel. Just like in octrees, what is done is, in voxel you have all the elements, all the squares which are used will have the same size and shape. Okay, there is no variation or there is no subdivision. Okay. In a typical this thing, what you do is, like I have a square, if I want to do a pixel representation, what I will do is I will take number of rows and columns. So, I have a two-dimensional matrix of pixels, and by saying whether a pixel is a part of the object or not, I am able to represent an object. Similarly, I take a cube, okay, divide it into smaller cubes. Okay. Like suppose if I have a cube of something like 10 by 10 by 10 size. If I take, let us say, my voxel element as 1 by 1 by 1, so I have something like 1000 cubes. Okay. The cube can be divided into 10 into 10 into 10, 1000 cubes. Now, I will see the object which is being represented, like I take each of the cubes and see whether there is a material in this cube or not. If there is a material, I can say it is a binary 1. If there is no material, I can say that this is a binary 0. So, simply you are going for a representation which is purely a binary representation. It has some similarities with octree method, and also there are certain advantages and disadvantages which you can clearly see. First thing is, in octree you are only decomposing further in terms of squares or cubes only if there is a material. Okay. So, that means the amount of cells which you end up in a octree would be less compared to a voxel based. Suppose if I take I have a size of an object is, let us say, 100 by 100 by 100, and if I am taking, let us say, a voxel size which is 0.1. So, you have 10 to the power of 9 voxels, that is 1000 into 1000 into 1000 voxel information which you have to store. So, the number of cells increases considerably. Okay. Whereas, in the case of octrees, you may not have that many cells, because there may be many cells which you are not further decomposing in the intermediate stage. So, that is an advantage. But like suppose, but there are some calculation conveniences. For example, I have converted, let us say, a solid, given solid into octree as well as voxel based methods. Suppose I want to quickly know what is the approximate volume of this object. How will I do it in, let us say, an octree based method? Is you first see what are all the cells which are there. Cells may be of different sizes. Okay. You say what are the sizes of, suppose if I take, for example, if I am calculating area of this thing, I can look at different cells which have different areas, count them, add them, and then you get it. If suppose if I have a voxel based model, all that which you need to see is that what are the cells, add all the cells and just multiply by the volume of a cell. So, little more convenient in terms of this. So, there are situations where voxel based decomposition methods, both octree and voxel, have many conveniences in terms of other methods. Like one very like I gave an example of volume calculation. So, if I want to know quickly, suppose I have a very complex object which has a free form solid, but I have a octree or voxel representation of that. then calculation of a volume becomes just simple multiplications and additions. There is nothing more. In fact, it can be purely additions or purely can say simple multiplications and additions. Whereas, if suppose if the object is a free form, if I want to do it by analytical or numerical methods, so I have to basically go for a numerical integration, use a numerical method. So that may be a little more cumbersome and process. In some cases, integral cannot be evaluated analytically, so you have to go for numerically, and numerical methods also have problems in some situations. You have to look at all those things, whereas it is very convenient in the case of this. Another area where octaries have large, can say, applications is in terms of intersection checking. Let us say I have two very complex solids and I would like to know whether these solids are intersecting or not. Now, suppose if I have, let us say, a voxel based representation of these two objects, how do you check whether they are intersecting or not? You are just you are interested in like knowing what is the whether they are intersecting or not, yes or no. So, suppose if I have a voxel representation, when can you say that the objects are intersecting? If there is even a single voxel which is common to both the objects, there is an intersection. So, you just have to look at voxels in both the cases and see whether there is any common voxel for this. So, that is as simple as that. Or if it is octree based representation, then you are checking basically an intersection of the cubes of one octave representation with the cubes of another one. So, intersection of cubes is much more convenient, like checking of intersection of, let us say, two cubes in a space is nothing but using only a relational operators, okay, like less than or greater than. It does not require any mathematical operation. So, computationally it becomes much more efficient to know whether there are any intersections between solids or also collisions. Collisions come when one object is moving in a space relative to the other. So, I can also, I know the sweep representation of a solid, I can convert into octree or voxel and quickly check whether there is any collisions which are happening or not. Like in many robotics and machine tool simulations, you need to check for collisions. So, one can build volumetric simulation based on octrees to quickly calculate this kind of situations. So, but imagine somebody has to build an object using a octree or a voxel based method. Okay. Given an object and here is my input to build the object, that is not a very convenient. Okay. It is not a convenient method of constructing an object. Okay. It may be a convenient in terms of storage, or particularly if I have to do certain computational geometry calculations, which may be like if I want to know what is the centroid of an object, I can very easily suppose approximate centroid of an object. Again, like if I use a free form representation, I have to do a lot of mathematical calculations or numerical methods. Here I can just use simple cube and other representation, other information to calculate approximate centroid of the object. So, in terms of computational efficiency, and they do not give you exact solution, because in most of the cases the octree or voxel based models are only an approximate representation of that. How approximate they are depends on how many cells one is going to choose or what level of subdivision which one chooses in the form of octrees or the voxel size in the case of a voxel based model. So, this is basically a voxel based. So, here you have the object is divided into 8. In fact, what is shown here is like all the cells are shown as a black, because it basically says that there is a material inside. But usually if there is no material, I am going to represent it as a hollow symbol, so that I can represent it as a complete tree like structure, a binary tree like structure to model a complex object. So, if we look at decomposition methods, this is not a convenient method for building objects, but this is good for like calculation of volumetric properties and intersection of geometric objects. One can also think of like we looked at two decomposition methods, octree and voxel based models. One can also think of there are methods which are called as cell decomposition methods, where you are dividing an object in the form of cells. Like you say that all the cells are made of parallelepiped, okay, box like objects, but they need not be of same shape and size. Okay. That is also a very common method for certain applications. So, cell decomposition is a special case of decomposition methods in which the cells which are used to model an object need not have the same shape and size as it is there in the octrees. Octrees you have the same shape, size can vary. In voxel you have same shape, same size. Here you are allowed to have both different shape and different size also as far as decomposition. So, this is like if somebody has to know what solid modeling is in brief, okay, is this. Okay. What we will do is we may have to look at some of these methods more closely, and because when we take up any of these representation for subsequent applications, okay, that would be useful, like methods like boundary evaluation and etc. We will do it little more in detail in our subsequent classes, and after that then we will take up some CAD/CAM applications based on the representations which we have studied for curves, surfaces and solids. Okay. So, I will just stop it here. If you have any questions, please clarify or ask.
So, in the two types of decomposition method that you have, that is one is octree encoding, other is voxel based modeling, which is the most commercially used option?
Okay, so your question is which is more popular? Is the octree based methods are popular or voxel based methods are popular? As such, both are equally popular. Like for example, in many of the volume intersection methods etc., people use octree based methods. Voxel based methods, basically one of the problems is the storage explodes as you decrease the size of the voxel which is used. Voxel based methods are very popular for mesh generation in CFDs. Okay. Suppose I have a computational domain and I would like to basically like in CFD you calculate what is called as area porosities and volume porosities in order to carry out the CFD analysis. So, in those situations, like I can use voxel based models. Octrees have also been used. So, that is okay. Any other points?
Voxel based modeling, voxel is filled partially.
No, in voxel based modeling what you do is, suppose you just check the center of the voxel. If center of the voxel is inside the object which you are trying to model, that voxel is considered to be completely full. Okay. So, this is an approximate representation. So, the resolution will tell you whether if the center of the voxel is outside the object, you say that that is an empty. So, all that which you need to check in order to convert into voxel based method is, first I have an object, then I have imposed let us say a voxel grid on the object, and then take each of the voxel points and check whether it is inside the object or not. If it is inside the object, it is filled. If it is outside the object, it is empty. All that is a binary. Okay, I think we will stop it here.